So, how does concentration affect the rate of reaction? Well, one studies it, one measures it, and one generates the so-called rate law. Rate law means, of course, experimentally determined. And the rate law is always of the form rate equals K times the concentration of reactant 1 raised to some power x, concentration of reactant 2 raised to some power y, concentration of reactant 3 raised to some power z, and so on. K is the rate constant, okay? Constant of proportionality. It's a terrible constant because not only does it change from one reaction to another one, within a given reaction it changes with temperature. So anytime you have to study the rate of a reaction, you have to do it using a controlled temperature environment. For us, that usually means you do it in a fixed temperature water bath. X, Y, and Z, those exponents of each of the concentrations, are called the order of reaction in each reactant. Okay. Now, normally, those just depend upon the reaction. They don't change as you change the temperature unless something massively dramatic happens. And so usually, when you study the rate law, you focus on the order to describe the reaction, and you'll only determine K for other reasons because, of course, K changes with temperature, and we'll talk about that in a later movie. Now we need to get a feel for what this rate means. Okay, for example, here is a reaction, a peculiar reaction. 4C plus 32D goes to stuff. Okay, now let us imagine that we have studied this reaction and we find that it's third order in C and fifth overall. So by what factor would the rate of the reaction change? The concentration of C was quadrupled, and if that of D were halved. So what we can immediately say from this information is the rate equals K. All rate laws start with rate equals K times concentration of C cubed, because I told you it's third order in C. Now I told you it's fifth order overall. Well, if the order with C is 3, then the order with respect to D, 5 minus 3, or 2. Okay? Now, I said that I'm going to quadruple C. Well, whatever I do to the concentration of C is going to have the effect on the rate as if I had cubed that concentration of C, because I told you it was third order. So if I quadruple the concentration of C, the rate is going to be affected by 4 cubed, which is 64. Now then, of course, D, right? What I said was, in this particular situation, I'm going to halve the concentration of D. Well, whatever I do to the concentration of D is going to do squared to the rate. And so halving the D quarters the rate. When I do these both things together, I do something that multiplies the rate by 64, and I do something that quarters the rate. Well, then the combined is going to be that the rate increases by a factor of 16, right? 64 times a quarter. Okay, so information in the rate law here that I gave you based on the order that tells you how the rate of the reaction is going to change as I change the concentrations. Do note, by the way, that the rate law, the parts in the rate law, the orders, these exponents have absolutely nothing to do with the coefficients in the main reaction. Let's do another example. 2a plus b goes to some other stuff, some different stuff. Now I'm going to flip it. I don't know the rate law, but this helps me get it. If I double the concentration of A, the rate doubles. If I triple the concentration of B, then the rate increases by a factor of 9. Well, every rate law starts off rate equals K, and then concentrations raised to the powers of their order. So in this case, I've got A, I've got B. They each have their own little order, X and Y. Now let's see what I'm told. Well, if I double A, well, then the rate doubles. Well, whatever I do to A is going to be done to the power of X as far as the rate is concerned, because the rate is related to the concentration of A to the power of X. Okay, well, in this case, I know that the rate increased by a factor of 2. So I double A, the rate changes by 2 to the power of X, and in this case, it doubles. That means that X is 1. Now look at the concentration of B. What I'm told is that when I triple B, the rate increases by 9. Well, whatever I do to the concentration of B is going to do to the rate to the power of Y. And in this case, we know that in the rate increased by a factor of 9 when b increased it by a factor of 3. So how do I raise 3 to a power to get 9? I square it. So y is 2. So this information here, by just changing the concentrations and see what effect that has on the rate, enables me to determine the rate law. Rate is k. I haven't done anything to get k yet. A to the power of 1, because when I doubled a, the rate doubled. B to the power of 2, because when I triple b, the rate went up by 9. And again, have to emphasize, the orders of the reactants do not come from the coefficients of the balanced chemical equation. So the last slide showed the mental process that you have to follow in order to determine the rate law. Now let's actually look at an experiment that you might complete. So our example, consider reaction 2NO2 plus 2H2 going to 2N2O2 plus 2H2O, determine the rate law and the value of K at the experiment, temperature of the experiment using the following data. So essentially what we want to do is get this rate law in which we're not only going to get X and Y, but we will then also determine K. Now the way you would do this is you would do several experiments in which you vary the concentrations. So you would know the concentration of NO2 at the start, you'd know the concentration of H2 at the start, and you would need to determine the rate. And the way you would determine the rate is that you would plot out the concentration of one of the species in the reaction against time. Thus you would have to be able to measure one of those concentrations against time. Now if we look at this reaction here, NO2 is a colored gas, H2 colorless, N2O2 colorless, and water colorless. So what we would probably do here is we would measure the color or the absorption associated with NO2, and as that goes down during the reaction, because of course NO2 will be used up, we will be able to follow it and measure the concentration of NO2, plot it against time, take that initial slope and thus get the rate. So in our first experiment we might take 0.25 molar NO2, 0.25 molar H2, and after plotting that graph we might find the rate was 2. Obviously these numbers are rather nice. Now the second experiment, we would need to change the concentration. If we were a good scientist, we would just change one variable at a time. So we might take 0.25 molar NO2, in other words, keeping the NO2 the same, and then we will change the H2, and let's be really clever and double it. And then we do the experiment, we'd measure the concentration of the NO2 by measuring its color, its absorption, plot out the concentration against time, and get that that instantaneous rate was 4. Now what we would do is we would say, well, what did we do here? From experiment 1 to 2, we doubled the concentration of H2. And what we saw happening was that the rate also doubled. So change the concentration of H2, change the rate to the same extent. In other words, Y, the order of the reaction for H2 must be 1. Okay? Because whatever we do to H2, we do it to the power of Y to the rate. And seeing as how when we doubled H2, we doubled the rate, that must mean Y was 1. Now experiment 3, what we would want to do is now change the NO2 concentration. So we'll take that up to 0.5, and we would want to keep the H2 either as 0.25 or as 0.5. So in this case we'll do it as 0.5. So we do the reaction, follow the concentration of NO2, plot the concentration of NO2 against the time, get that initial rate, and we find it is 16. Well, let's see what we can do to explain that. The NO2 doubled, so whatever is going to happen to the rate is going to be doubled to the power of X. And what we find happened to the rate was it went up by 4. So 2, the doubling to the power of X, equals 4, thus X must equal 2. So now we've got the orders. Rate is K times concentration of NO2 squared times concentration of H21. How do we get K? Well, we can get K in actually 3 different ways, because K is now the only unknown in that equation, and we have 3 sets of data in which we know the rate, the NO2, and the H2. Now some people would just use that once, so let's say experiment 1. Rate was 2, K we don't know. Concentration of NO2 is 0.25 and we know that's squared. Concentration of H2 is 0.25 and we know that's to the power of 1. So we can rearrange that and get that K is 128. But K should be the same for all of those experiments. That's the whole point in what we're doing, that K is staying the same because we're doing the experiment at a constant temperature. So therefore, not only could we use any of the 3 sets of data to determine K, but as a careful person, you would use all 3 sets of data to determine K. So we'll take experiment 2. Experiment 2, the rate is 4. Concentration of NO2 is 0.25, concentration of H2 is 0.5. Pop all that in and we get K as 128 again, so we're rather happy. But let's do it with the third set of data. Rate is 16, concentration of NO2 0.5, concentration of H2 0.5, pop all those in, and again we find K is 128. So we can say that for this particular reaction, rate is equal to 128 times the concentration of NO2 squared times the concentration of H2 to the power of 1. Hopefully you enjoyed that. However, those numbers 0.25, 0.5, 2, 4, 16, probably not ones that we would get in a regular experiment. So let's do a new one. Consider reaction A plus B plus C. So now we got 3 reactants going to stuff. Determine the rate, law, and K using the following data. So I'm not going to fill it out with the discussion, but this is what we get. Okay, so there's our concentrations of A in 4 experiments, B in 4 experiments, C in 4 experiments, and there are the rates that we get. Now what we're trying to get is, of course, the rate law, which always starts rate equals K, then the concentrations of the reactants. We got A, we got B, and we have C, all raised to the powers of their individual order. And so what we need to do is we need to get X, we need to get Y, we need to get Z, and we need to get K. Now when you look at these, if you're sort of hot with numbers, you can see the relationships there. But other people might not be so hot. What's the relationship between 0.491 and 0.648, for example? Okay, so when you've got nastier numbers like this, there's 2 processes you can try. I particularly like the one in which you set up so-called simultaneous equations, because all 4 of these experiments with their A, their B, their C, and their rate have the same K, X, Y, and Z. So we can plug in these numbers into the equation and get 4 equations that have all got the same unknowns in them. And then we solve them simultaneously. Or simultaneous is actually because they all simultaneously have the same variables. So take experiment 1, put in the data. Rate is 1.22. There's K, we don't know it. The concentration of A, 0.162, raise that to the power of X. Concentration of B, 0.252, raise to the power of Y. Concentration of C, 0.422, raised to the power of Z. Take 2, 3, and 4 experiments and pop those in. Make sure you see where I'm getting all those numbers from, but it's not tough. I'm essentially just taking the material out of this table and sticking them in to that equation. Now when we look at these, we should be able to combine a couple of them so that we lose all but one of the unknowns. Have a look and see which equations have got matching pairs. And I would start with saying 2 and 3. Okay, the rate's different, K's the same, X is different, but the Y and the Z are the same. So if I take them and I divide them, then I can anticipate being able to cancel out all the known bits. Now I would also divide them putting the big numbers on top. So number 3 has got 11.03 as the rate, 2 has got 4.9 as the rate. So let's just set that up. 3 divided by 2. Make sure you see how I've got this. Okay, there's 3 on top, there's 2 on the bottom. So cancel out the K's, cancel out the 0.503s to the Y's, the 0.422 to the Z's, and what I'm left with is 11.03 divided by 4.9, which comes to 2.25, is equal to 0.491 to the X divided by 0.325 to the X. Well, as they're both to the X, we'll just divide those in, and we get 1.51. Okay. Now, how would we solve this? Well, you have to use logarithms when you've got an unknown power. So what we would do is we would take logs, and so the left-hand side becomes log of 2.25. The right-hand side is now x times the log of 1.51, because when you take it to the power, it becomes times. So x is going to be 1.97. Now, these are experimental data. You don't expect it to be beautiful. So we could say x is 1.97, but orders are nice numbers just about all the time. They're whole numbers. They're certainly not going to be something weird like 1.97. So why don't we just say that's 2? So now we know x equals 2. The order of A is 2. It is second order in A. And everywhere we see x, we can replace it by 2. Okay? Now we know that. Let's see if we can combine a couple more equations to eliminate now 2 of the remaining 3 unknowns. And if you look at those, I hope you would see that 1 and 2. They've got different rate, they've got the same k, got different here, but who cares because we know what this is now. They've got different to the power of y, but they have the same to the power of z. Again, big number on top, so 4.9 on top, 1.22 on bottom. Now let's see what we do here. K's cancel, the 4.422 to the z's cancel. We can calculate what this is, the 0.325 squared divided by 0.162 squared. So let's see what we've got. 4.9 over 1.22 is 4.02. 0.325 over 0.162 squared is 4.03, and then 0.503 divided by 0.252 is 2 raised to the power of y. So 2 to the power of y is 1. How do we get 1? By raising 2 to a power. Y must be 0. So now everywhere we see y, we can put 0, or of course everything raised to the power of 0 is 1, so we can actually ignore everything to do with b. B does not appear in the rate law. Okay, now the last twos we got k's and we've got z's. What shall we combine to get rid of those? Well, now it actually doesn't really matter. We've just got to combine ones where the z's don't cancel. So it has to involve 4 because that's the only one with a different z term in it, but we could take any of 1, 2 or 3. So I'm just going to take 4 divided by 1, big number on top again. Notice now there was no now blue term because that was y is 0. Again, we know the x term. Right, the a term there is squared. We can cross out the k's. We can say that this turns into 8. This 0.648 divided by 0.612 squared becomes 16. So we get 0.5 is 0.5 to the power of z. Thus z must equal 1. Okay, so by putting in the data in equations and then combining those equations to eliminate all but one of the remaining unknowns, we're able to find out its second order in A, it is 0 order in B, and its first order in C. Now the last step is, again, we wanted the value of k. So can again use any of these data points. I will use all of them. So pop in the data and now solve for k. First one, 110. 110, 108, whoops, 110. Well, that's the nice thing with using all of the data points there. You can just take the average and we can get that the rate law is such that rate is equal to 110 times the concentration of A squared times the concentration of C to the 1. Get used to doing those. They can get complex, but I think they're kind of fun. And so we will certainly have a couple on the homeworks, the workshops, and even the exam.